My presentation today is about formal methods and continuous change, or software engineering practice, towards a happy marriage. We'll see whether the happy marriage can get consumed in the end. So let's move to the outline of my presentation. I will first talk about the real intrinsic relationship between software and change. I will then focusing on changes that occur when systems are executing, running, after we deliver them. And this is what leads to runtime adaptation to be able to deal with these changes. And as I believe, a complete rethinking of the way that execution is supported today in software. And in doing this, I will mostly focus on some of the lessons that I learned in a project that I led for the past 5 years, which was funded by the European Research Council, which was exactly on runtime adaptation. And then I will speak more broadly in terms of what I believe that is the disappearing boundary that we have today between development time and runtime. This notion is known in the practitioner's work under a buzzword which is called DevOps, development and operation, and which looks at software as continuous evolution. And we will talk about the verification challenges that we have here. So basically, in the end, what I believe is that I would like to propose a holistic view of both the runtime operation of software and the development time in which verification plays a fundamental role. Models and verification, they drive the evolution, both at runtime and design time. In a holistic way. Okay, so software and change. I think we all know that among the technologies that we have in our world, software is the technology that undergoes continuous change. There's no other technology that does that, so it's really unrivaled by other technologies, and it can be a problem. Actually, it has always been perceived as a problem. What I actually believe is that this is more than a problem, it is an opportunity. So the fact that software can evolve and has to evolve and we can support evolution really is the main, one of the main values of software. So it can be an opportunity. And in fact, I would like to propose that, in all of this, we have a positive view of change. Change has to embed the notions of improvement and adaptation. And, this is evolution, the human evolution. It actually embodies those two notions, that, humans adapted and they improved over time, and software can be the same. So the message that in the end I want to pass is that formal methods can be integrated in the software engineering practice to effectively and efficiently turn change into this positive view of evolution. Before we do that, however, I think that we need to rethink for a while at what are the main drivers for evolution. So why is software changing? And to do that, I would like to briefly summarize to you a contribution that was given, pretty long time ago, in the end of the 90s, by a paper that I think is one of the nicest papers that I've read, which, can be seen as one of the papers that gives foundations to requirements engineering. So this is a paper by Pamela Zave and Michael Jackson, which appeared in the ACM Transactions on Software Engineering Methodology. And in brief, let's see what they say. When we develop software, what we actually do is that we build abstract machines. And those machines that we build have to achieve real-world goals and have to satisfy certain requirements. The goals and the requirements originate in the real world. So we have to look at the real world to identify the goals and the requirements. But we develop a machine, and the machine can satisfy the goals, can satisfy the requirements under certain assumptions about the environment in which the machine eventually will be embedded. So there's environment assumptions and properties that bridge between the machine and the world. And thanks to those environment properties and assumptions, we can prove that the machine actually achieves the requirements that we want to satisfy in the real world. Let's be more precise. So here we have these three things, which is S, the machine. I call S because basically I mean the specification of the abstract machine, and of course the implementation. Then we have R, the requirements, and E, which is the environment assumptions. So basically, what is the responsibility that the software developer has? The responsibility is to actually develop a specification for the machine, and then eventually an implementation, such that, assuming that the environment behaves according to E, we can assure satisfaction of R. Okay? It might look a little bit too abstract. I will give examples. But before doing this, I would like to state this in a more formal terms. So formally, we can say that E and S entail R. So given that the environment behaves according to E, and given that the machine satisfies S, then we can prove that the requirements are satisfied. And this is actually the main, what I call the dependability argument. This is the responsibility that a software designer has when a software system is designed to make sure that this relation is satisfied, that this argument is demonstrated. So, where is evolution? Why do we have evolution? Well, the drivers for evolution are in each of these three elements. So, first driver is getting the machine right. Building the right specification, building the right machine. We all know that there is no way to get it right in the first place. So it is an iterative process. Software design is exploratory. Software evolves continuously as you are developing it. So there's an intrinsic nature of evolution here. But there is another source of evolution, which is in the requirements. Because the requirements are highly volatile. We know, I mean, everybody knows that requirements change continuously. First of all, they are hard to get. So they change sometimes because what you get in the first place are wrong requirements or not exactly the right requirements. So they're hard to get, and they change rapidly in any case. So the point is that, you know, if requirements change, you might break this relation, right? So it was true before, it's not true anymore, which means then that you have to change the machine. So this is a driver of evolution. Third driver, which is most important, and actually we'll focus on this, is the environment. Getting environment properties and assumptions right is hard. And I wish to distinguish between actually the properties and the assumptions. Okay? What are the properties? Properties are laws of the domain in which your application lives. So, for example, the laws of physics. So for example, you know that to move a body, suppose that your requirement is to move a body from A to B. Then the domain property that you use is a law of physics that tells you that if you apply a force in the direction from A to B, this causes a motion in the direction A to B, right? So the specification for the machine to satisfy the requirements based on this domain property is that you send a suitable command to an actuator that generates a force in that direction, and we will achieve the goal of moving the body. Okay? So, well, of course, properties are by definition true unless you disprove them, unless you disprove Newton's laws or the laws of mechanics. So we can assume that they are true. But, sometimes we also use assumptions. And what I call by assumptions are properties that may be disproved later. And very often we have to do that. So assumptions they represent uncertain, incomplete, changeable knowledge. Suppose here that your requirement is to guarantee a given average response time to users. Okay? Your domain assumption that you may use is that the average traffic is of X transaction per millisecond. Then under this domain assumption, you may, So under this assumption, you may be able to prove that your software guarantees a required response time to users. But you never know whether the average traffic of X transaction per second will actually characterize your environment behavior. It may be true in the past, it may be true at some given point, it may change later. But, for example, assumptions about traffic are assumptions that people normally make when they design systems to guarantee certain response times. But those assumptions may be disproven later. So getting the environment properties and assumptions right is hard. And so very often you hypothesize wrong properties or assumptions. Often the assumptions that you make at design time are uncertain. Often assumptions change. So, which means that, again, if E changes, the relationship may be broken. And again, you need to change the machine to keep the relation satisfied. So, there is a notion of failure of satisfying the dependability argument that I'm talking about here, right? And when I say failure, of course, I don't mean necessarily that it's a catastrophic failure. It's any deviation from the requirements. For me, that's a failure. You have requirements that tell you what you have to achieve. If you don't achieve what is specified there, that's a failure. Okay? And of course, I'm using a view in which I talk about both functional and non-functional properties. I'm talking about quality of service, for example, like in the slide before. I'm talking about response time that you have to guarantee to your users, not necessarily a given functionality. Now, in particular, let's dig a little bit into a particular kind of system that is very common today. Very commonly today, we build systems that I called multi-owner. I think that we have been talking today with several people, and this is very common in all areas. So we build systems, putting together parts that we don't necessarily control, that are owned by others, they are run by others in many cases. So for example, consider the fact that we develop software and we run the software on the cloud. We don't own the cloud. We just hire time to run our software on the cloud. we use software as a service. So for example, we write applications in which we use Google Maps for geolocalization and use the APIs that are provided by Google Maps. We don't run Google Maps. So in systems that are multi-owner, I think that there was a famous sentence that Leslie Lamport made years ago about distributed systems, saying that a distributed system is a system where I can't get my work done because a computer has failed that I never heard of. And you can generalize this to multi-owner systems. My application fails because there's a piece that I don't control. So this is becoming more and more common. Now, how can environment changes? So I will focus mostly on changes in the environment. So environment changes, first of all, terminology. I call the evolution due to environment changes as adaptation, okay? So I'm not talking about requirement changes. I'm mostly talking about environment changes. So there has been, in the past, a quite active area of research about software systems that can self-adapt at runtime, and in particularly focusing on so-called continuously running systems. That is, systems that we deliver, they're there, we cannot stop because they are, for example, on a satellite, and they have to adapt. We have to adapt them. So, and as I said, mostly what I say here is based on some of the experience that I developed. And this view has been popularized years ago by the so-called autonomic computing approach, where you see that you have the real world, you have sensors and effectors, and then what the software does is monitor, analyze, plan, execute. So you have a kind of feedback loop here. So you get data from sensors that can tell you about changes that are occurring in the real world, and then you are reacting to those changes. Basically, what I claim is that the whole this whole feedback loop should be based and can be based on modeling and verification, so on formal foundations. And this is what I briefly try to do now. So briefly, what a self-adaptive system has to be able to do is detect exogenous changes, so things that occur outside that denote a change, understand, reason about those, and understand whether they can lead to requirements violations. If they do, react. React by changing behavior, by reconfiguring the application. So monitor, analyze, react. Claim is, and basically a summary of the experience that we got in the project that I mentioned, is that you need formal methods to also migrate to runtime to support this view. So you need the model of the environment and the model of the machine, S and E. They are not only artifacts that you build when you develop your system, but they have to survive, they have to live at runtime, first. Second, the model of the environment has to be updated by monitoring and applying some kind of learning. So you monitor low-level events, you abstract from those level events into significant events at the model level. And then, when you have this change, you have to apply a verification step. So formal verification at runtime checks whether the dependability argument continues to be satisfied. If not, you trigger an adaptation. So that's let's say, the life cycle. I mean, there's a number of papers that, if you're interested, in which we explore more about this. And I would like to give you a small example of a system, kind of abstraction. And in particular, the systems where this can really, we have tried in several cases to apply, is systems in which the requirements are quality of service requirements, non-functional, like performance, response time, reliability, probability of failure, cost, like energy consumption. And the framework is the following. You have a system which integrates external services, and it's used by users. For these systems, the sources of uncertainty are, first, in the behavior of users. You don't directly the user profiles, how users, among the various functionalities, which functionalities they use more than others, for example. Uncertainty is in the behavior of those services, as I said before, because they are run by other owners. They may change them, they may update, they may install new functionalities without telling you. So there's a lot of uncertainty there. So, in particular, we have done, I will at least here, focus on requirements that you can specify in probabilistic terms, and system models that you can specify through probabilistic models. In particular, I'm assuming that requirements here are specified, formalized, using some kind of probabilistic logic. And in particular, I'm using PCTL, which is probabilistic CTL, is a probabilistic version of temporal logic CTL. And I'm supposing that the model of the system is specified in terms of discrete time Markov chains. So state machines with probabilities on transitions. And for example, for a system, a property like the probability that a given workflow leads to a success state can be specified, in a temporal logic property that says that the probability that eventually you reach a success state is greater than 0.98. And of course, we know that there's tools also that can do the verification for you, although we will say, as they are not entirely suitable for use in this kind of context. But a tool like Prism, developed by Marta Kwiatkowska at the University of Oxford, can do this kind of verification for you. So, simplified case study. Suppose that you have an application in which is an e-commerce application. So you have people who log in, they search for items to buy, then they buy more, and then when they're finished, they can ship, and there's two choices, normal shipping, express shipping, then they check out and log out, okay? So, suppose that in the requirements, you have a requirement that distinguishes between two kinds of users, returning users, who are using the system very often, and new users. And you want to provide better service to returning users than new users, casual users. So suppose that you have requirements like, the probability of success of a session in which a transaction from login to logout is greater than 0.8, and the probability of an express shipping failure for returning customers is less than a given value, okay? To develop a system, you have to make a number of assumptions about the environment. Here is an example of what I said before. So, for example, you have to make some assumptions about user profiles. For example, what is the probability that a user is a returning customer as opposed to a normal customer? What is the probability that a returning customer chooses to do express shipping as opposed to normal shipping? So these are examples of requirements on the user profiles. But you also have requirements on the behavior of external services that you have examples of properties, assumptions about the external services that you have to make. Like, what is the probability that the login service fails? I forgot to tell you that I'm assuming that, here in this workflow, the gray boxes here denote external services. So there's a service that you integrate in the workflow that does the authentication of users, login. There's a service that you integrate in your workflow that does shipping, normal shipping, and there's another service that does checkout, so payment. You use the credit card service. So these are services that you integrate here, and you're making assumptions about their probability of failure. What is the probability of failure of the authentication service? How do you make these assumptions? Based on experience, based on past observations, based on rules of thumb. But they are uncertain. Plus, they may change. For example, user profiles, depending on the season, it may be that you are around Christmas, there are certain profiles because people buy more. In other times of the year, there are different profiles. So even if you know them, they fluctuate, and you don't know how much. But let's see, what is the specification of the machine? Actually, this is a machine that incorporates both the specification and the behavior of the environment. Because, for example, and this is a DTMC, is a state machine with probabilities, right? So you have this initial state, and then in which you do login with probability 0.97. These are the probabilities that come from the tables that I showed before. Probability 0.7, it succeeds, 0.3 fails, and so on and so forth. Here is a state machine, and this is the success state. And you want to say that the probability of reaching the success state is greater than 0.8. And the probability of a failure is less than that. Well, if you run the model checker, it is satisfied. But what happens then? Suppose that you design your system and the system works. So at design time, you did your job. Now the system goes to runtime. Well, you want to, again, as I said before, to continue to say that, suppose that one of the probabilities that I have here changes. So the probability of failure is actually higher, or the probability that users are of a given kind as opposed to the other kind, it changes. How does this affect the satisfaction of the requirements? So you need to update those probabilities, recheck the verification, and check whether there is a violation of the model. Okay? So in this case, in particular, suppose that these two probabilities change. So profiles of users change. How do you detect them? Well, you monitor the behavior of the environment, then you have some kind of Bayesian type of learning process that retrofits the data to probabilities that you have here. And then if you run the model checker, it may be that it may happen that your requirement gets violated. Now, before saying how you react, the thing that I want to discuss with you is this actually viable? Can you bring the model checker to runtime and continuously rerun the model checker to check whether the requirements are violated or not? Well, there's a challenge here, which is basically what I say here, that we have to be able to make the model checker at runtime efficient. The normal approaches that you follow when you do model checking is that you rerun every time the model checker from scratch. But if you do this, it may be that the time needed to react and the time needed to reanalyze the model are in conflict. So you cannot react promptly because the time to reanalyze is too high. But what actually happens is that changes are normally local. It's not a global change that invalidates the model. It's exactly the change at that particular point that happens. So the idea is, instead of doing model checking from scratch after every change, can we make it incremental? Can we take advantage of previous analysis? Well, it turns out that it's easier to say than do. Actually, one of the approaches that we experienced is what I call incrementality by parameterization. Okay, so that's a way of making verification incremental. Basically, what that says is, suppose that you can anticipate where changes may lie in your model. And often you know, because these are the places where you have uncertainty. So suppose you know where they are. And suppose that you can cast those changes by representing, instead of values, using parameters. So using variables. So for example, in our case, what you don't know are the actual values, or what can change are the actual values of probabilities that you have on certain transitions. So instead of saying 0.98, you can say, I don't know, X. So you call it X. Okay? Then what you can do is, at design time, what you do is you produce a verification condition. So you produce a formula that has to be satisfied once you know the values of those variables. So model checking that you do at design time is a mix of numerical and symbolic computation. So it's a mixed execution. Okay? The interesting thing is that let's concentrate on so-called reachability formulae that you have on DTMCs. So the probability of eventually getting to a certain state. Okay? Reachability formulae can be expressed as polynomial formulae. It turns out that, if you do the analysis, okay? So what it means is that the verification condition is a polynomial. And the polynomial is the only thing that you have to bring to runtime. So once the values of those variables become known, you just substitute the values in the polynomial form, and you get the value of the probability. Okay? So this gives you a very efficient way of doing analysis. Okay? So actually, this approach, a student of mine, who would develop this approach, called this approach the working mom paradigm. Because working moms, they prepare food for the children, they freeze them, and then when they need it, they take it out, and they just, defrost it. Okay? And that's the similar approach. You pre-compute the verification condition, and you leave it symbolic up to the values that you need to fill in at runtime. Now, where are we? So this is a way. During this project, we understood, I think, how to be able to bring models to runtime whenever to support self-adaptation. To support self-adaptation, you need to bring the model and the formal verification to runtime. But to do that, you have to rethink about the verification engines to make them incremental if you want to keep with the speed of change that you have in the environment. Can we go beyond that? So can we think not only of the runtime changes, but of the whole process? When you're developing the system, you have continuous change. Then you go to runtime, the system is able to self-adapt. Maybe not everything can be self-adapted. It has to be fed back to development. And then again, development becomes incremental. Can we have a view that takes all this process, development and operation, and tries to fund this on models and verification? So the change of perspective is, as I said before, the complete DevOps life cycle. Well, to do that, I want to open a brief parenthesis. So all this continuous development is often, characterized under the umbrella of agile methods. So this continuous development style. Okay. And there's a nice book, if you don't know it, by Bertrand Meyer on agile methods, which is called The Good, the Hype, and the Ugly. And what he says is that, what is the ugly? The ugly is exactly what I'm talking about here. The lack of stress of what they call upfront activities. Actually, they deprecate upfront activities, that is requirements, modeling, verification. So requirements, they say, no, requirements are useless. Well, I'm kind of exaggerating here, okay? But requirements, they should be replaced by user stories. Specification actually is replaced by test definitions. They say that tests are the specification, the tests that a piece of software has to pass. Okay? Modeling, useless. I mean, it's just a waste of time. So this is the ugly, I think. But there is good here. The good is that they actually think of, let's say, quality assurance, continuous quality assurance. There's this idea of continuous testing, continuous, actually it's called test-driven development. So my claim, actually, is that we should be able to get rid of the ugly and move the good one step further. So get rid of the ugly means that we have to make sure that what they call upfront useless activities, actually they are useful. Modeling is useful. It is useful as long as you can verify the model, which is what I think that should be done more. But the model should be verified in an agile manner, which means that you have to be able to do the checks incrementally. So verification. So in the end, what I'm saying here is that the whole agile approach can become a reasonable, let's say, development approach, development and operation, if we can really integrate modeling and verification into the process. And in the end, instead of having a test-driven development, we will have a verification-driven development, which moves actually one step further. So what needs to be done to do that? I really believe that most of the modeling and verification tools that have been developed so far, to really go in this direction, they really have to support incremental reasoning. They really have to support incremental analysis. Because what the designer needs is to be able, after any change, to understand the effect of that change. And the reason why modeling and analysis so far have been viewed as, let's say, antagonistic to agile development is because most of the tools that we have today to do modeling and analysis actually require you to do this from scratch every time. They are not incremental in nature. So there's a lot of work that is now going on about supporting, for example, incomplete, partial specifications, so that you can incrementally add new knowledge. But still, even in the incomplete stage, you can do analysis. So this is a very interesting area. We have also been doing some work on this. And the idea is that, for example, normally verification tools that run on a complete model, they have two answers. Either the property is satisfied or the property is not satisfied. And in many cases, you're also given a counterexample. For example, if you have model checking. But if you have incomplete models, then what you actually want is to be able to get more. So if the model you give a model that is incomplete and you give a specification, it may be that the property is verified, and then you get yes. It may be that the property is not verified independent of the way you will complete your design, and then you get no. But it may happen that you don't know. So it's maybe. Maybe means that if you have an incomplete system, it depends on the way the incomplete parts will be completed. But in that case, what I would like to have is not only someone telling me that maybe, but maybe also tell me what has to be satisfied by the missing part. What is the proof of obligation that I have to fulfill for that part once I complete it, instead of redoing the check of the entire system? So, we have, for example, we have been doing some work here, on, label transition systems and LTL, and temporal logic, and the point is, whether eventually you can reach this state without going through this state here, in which you have a part of the system that is unknown. And and actually the approach that we have is able to tell you yes, in case you can, no, in case you can say that no matter how you complete your part, the property will always be violated, or it may tell you maybe. And in that case, it tells you, but, maybe, and this is the constraint that has to be satisfied by that unknown part to make the whole property satisfied. So I'm not going through this. I'm just skipping because the other thing is that so partial models lead to incremental changes. But in general, what I would like to have is a theory that whenever I have a model S and a set of properties that have to be met by S. I'm stating this in informal terms. Whenever I have a change then, which is a new pair, S prime, P prime, new system, new property, where S prime is, let's say, is S plus delta. I'm very informal here, right? Plus delta S, and P prime is P plus delta P. And suppose that I have a proof of S against P. The proof P prime of Pi prime of P prime against S prime can be done by just doing a delta pi, such that, pi prime is equal to pi plus delta pi. So that's the whole goal. And I would like to be able to develop. Now, I'm done. But actually, we are trying to do this casting verification to a syntactic semantic approach that is based on, I'm just mentioning this. I mean, if anybody here remotely has any interest in this, I would be very happy to send material. But, trying to cast this into, let's say, a general formalism, which is called attribute grammars, that goes back to Knuth in the old times, which is, a very powerful formalism, which can encode, basically, any kind of specification, any kind of property, and cast the proof in terms of propagation of attributes, and this can be done incrementally. So the idea is that through this, maybe, we will be able to develop a kind of generalized framework to support incremental evaluation. I just want to show this because, it's not my work. I mean, it's the work of many people. These are, some of my past PhD students. We got together for a celebration that I had in Zurich for ICSI a couple of years ago. This was ICSI last year, again, with students of mine. So there's generations of students that have been working on the whole set of these things, and I need to thank them for what they did. Okay? Thank you very much.